All right, here we go. Last section, chapter 8. A lot going on. So, um, if you're watching this at excessive speed or skipping through it, now's not the time to do it. Now's the time to sit back and watch this at regular speed and take it all in. Estimating a population mean. When do we think mean? Mean means average. When do we think taking an average? Quantitative data. So, this is how we construct confidence intervals to estimate the population mean when all you know is sample data. So, major problem right here. What is sigma? Sigma is standard deviation of the population. How can I know the standard deviation of a population if I know nothing about the population? All I know is sample data. We now, for the first time in this class, are creating a new distribution. What is a distribution? Up until today, it's been the normal curve. We've talked about normal distribution, normal this, normal that. We now are going to talk about the t-distribution. So, when the sampling distribution of x bar is close to normal, we can find probabilities involving x bar by using our z-score formula. Sample mean minus population mean divided by standard deviation, sigma over square root of n. We learned that formula last chapter. But what happens is, when we don't know sigma, which you really won't, who would know this population standard deviation when you're dealing with a sample data? How could you possibly know that? What happens? We have to use the sample standard deviation. What happens when we use the sample standard deviation? We get the t-distributions. And notice how I say distributions. There's one normal curve, but there's many t-curves. When we standardize based on the sample standard deviation, Sx, our statistic has a new distribution called the t-distribution. It has a different shape than the standard normal curve. It is still symmetric. It is still single peaked. It looks almost the same, but what changes is the tail areas. See, let's take a look. A t-distribution has more area at the tails. A normal z curve is more tight in the middle. More tail area. What does that mean to us? Think about it. If you don't know the standard deviation of the population and all you know is the standard deviation of the sample, it means you know less. What happens when you know less in statistics? It means you're more uncertain. What happens when you're more uncertain? You need to give more room for error, more wiggle room. How do we give more wiggle room on a curve? Put more area at the tails. So, like any standardized statistic, t does still tell us how far x bar is from the mean. It is still standard deviation units. So a t-score is still how many standard deviations it is from the mean. Remember, z-scores were like 1, 2, 3. T is the same. It could still be 1 standard deviation from the mean, 2 standard deviations from the mean. What is different? Why is there t-distributions? Because with every sample size, there is a different t-distribution. It is called degrees of freedom. So every sample size, if the sample size is really small, you have a lot more unknown. So the t-distribution will give more area at the tails. When the sample size is larger, the t-distribution will get closer to a normal distribution because the bigger the sample size, the more you know, and the more you know, the closer the distribution can get to the normal curve. How do I get degrees of freedom? Easiest thing on the earth. Sample size minus 1. When we perform inference about a population mean mu, so what does that mean? It means we're trying to estimate the unknown mean of a population. We use a t-distribution with sample size minus 1, degrees of freedom, df, degrees of freedom, sample size minus 1. So, here's the summary. You take an SRS of size n from a large population that has a normal distribution with mean mu and standard deviation sigma, we get to use the t-curve to make our approximations. So we take our sample mean, subtract our population mean, divided by sample standard deviation over square root of n. And each one of these will go with its own t-distribution with n minus 1 degrees of freedom as long as the sample size is large enough. What do I mean by different t-distributions? Take a look here. The standard normal is the purple one. Purple one's the lowest, the least tail area. As the degrees of freedom go up, we get closer to the standard normal, meaning less tail area. 9 degrees of freedom, but look at 2 degrees of freedom. A lot of tail area. Why is that? There's more unknown. They are still density curves, so the density curves for the t-distribution are definitely similar. The spread of the t-distribution is simply a bit more, meaning more room for error. The t-distribution, more tail area, I've said that. And degrees of freedom goes up. The distribution looks more like a normal distribution. Here we go, problem, let's do it. No, last chapter we found z-stars. We found a bunch of z-stars using inverse norm. Well, what critical value t-star, because now we're using a t-distribution, should be used for constructing a confidence interval for population mean? So here we go. We're going to need more information. Last chapter, all we needed to know was last section, all we needed to know was how our percent was. Was it 90? Was it 95? Was it 99? Well, in this section, we also need the degrees of freedom because we are using a t-distribution. So, what is that for us? Our first one will be a 95% with 12 as the sample size. Sample size of 12 means 11 degrees of freedom. I'm going to show you how to do it with Table B. Table B is the t-distribution table. The back of the book has Table A and now Table B for a t-curve. I'm going to show you how to do it on the calculator also. So do you actually have to use the t-distribution table? Not really. If you have a TI-83, that's the only reason, but you can download Graph and Calc 83 app, and you won't need it. But I'm still showing you anyway. The table asks for how many degrees of freedom, and then it asks you what's the tail end probability. Remember, from last section, 95% is the center 95, so there's 2.5% on each tail, and you would just find where they overlap. Sample size 12 is 11 degrees of freedom, and you would find your t-star. I'm going to show you how to find this on the calculator, which is, of course, much more condoned for us because we are a calculator class. If it can be done on the calculator, we do it on the calculator. So, quick summary again. We are finding estimate for mu. The data is quantitative. When it is, we use in a t-distribution. So I'm looking for second vars, distributions, right? This is where we found inverse norm forever. Look right below it, inverse t. What's it going to ask for? What's the tail area? For 95%, that's 2.5% on each tail. What's the degrees of freedom? 11, because we had a sample size of 12. Paste, enter. There is how you get your negative 2.2. Look at that, negative 2.2. We see t here, 2.2. Why did they drop the negative? Because we always drop the negative. Z-star, if we found the left tail, it would be negative, we would drop it, right? Because look, I could do inverse t, second, vars, inverse t. And if I really want the positive, instead of just making it 0.025, I make it 0.975 to get to the positive side of the curve. See? We care about the positive version. They are exactly the same. This is the left t-star. This is the right t-star. But in general, you just use the positive version. Okay? Let's do a couple more while we're here. So second distribution, inverse t. Let's say we had a 90% confidence interval. 90% confidence interval, 5% is the tail. Let's say our sample size was 20. It would be 19 degrees of freedom. And you would get your t-star for 90% confidence interval, sample size 20. Drop the negative. 1.73. That's how it works. You get your t stars by taking the positive version of an inverse t. Moving right along. Okay. One hitch with the t-table is the t-table, after it gets to bigger degrees of freedom, it starts to jump 30, 40, 50. The calculator, you never have to worry about that. If your sample size is 33, you can use 32 degrees of freedom. The table is harder because you always have to round down. If you have 48 as your sample size, you have to use 40 because you always have to err on the side of caution. I don't suggest anyone in this class uses the t-table because you either have your graphing calculator or you can use the Graph and Calc 83 app, which will do this for you. So there's no real reason to ever use table B. I repeat, there's no real reason. If you do really want to use it, you have to just remember to round down your degrees of freedom when they get to the large numbers bigger than 30. Okay, again, T versus Z. T is for means, Z is for proportions. Always, never an exception. You will never use a Z for a population mean. You will never use a T for a population proportion. All right, so we had some conditions to do inference for proportions. They were random 10% large counts. Well, look at this. Conditions for doing inference. Random. The data still has to come from an SRS or randomized experiment. 10%. The population still has to be 10 times larger than the sample whenever you're sampling without replacement, and that is for the standard deviation formula. Still the same. Large counts. Okay? Large counts is not n times p, n times 1 minus p greater than 10. Okay? Because we don't have a p. So what is it? It's what we learned last chapter. We learned that the population has a normal distribution or sample size at least 30. Population large greater than 30. Population normal or sample greater than 30. Now, there's a third part to this. It says it right here, right? Number 1, normal distribution. Number 2, sample size greater than 30. Number 3, if the population distribution is unknown shape and n is less than 30, use a graph to assess normality. Believe it or not, you have done this many times. Think to yourselves, what graph did I use in chapter 2 to see if data was normal? I did it on my graphing calculator. It was a stat plot. I remember Mr. V or Mr. Walsh saying, based on the linear trend of the normal probability plot, the data are approximately normal. Yes, we can check data. If the sample size is smaller than 30, we can check for normality by doing a normal probability plot. So let's construct a confidence interval. We just check conditions. What is the name of the test? The name of the test is a one sample t interval. One sample t interval. So when the conditions for inference are satisfied, random, 10%, large counts, the sampling distribution for x bar has a roughly normal distribution, but because we don't know sigma, we have to use standard error, like we learned last section. So replace sigma with sx. Sx over square root of n will be our standard deviation called standard error for this confidence interval. Remember, to construct a confidence interval, we need to have a critical value, a standard deviation, and a point estimate. So what does that look like here? Statistic will be the sample mean, x bar. What is the critical value? It is t star with degrees of freedom n minus 1. What is the standard deviation? Sx over square root of n. This is the formula for our confidence interval. We will do it on the calculator. You got to know your formula also, but you don't have to do it in a question. Here we go. The one sample t interval for a population mean is similar in both reasoning and computational detail to the one sample z interval for a population proportion, but we just substitute in the new stuff, meaning the confidence level gets us the t star, standard deviation, point estimate. We drop the negative off t star because the plus minus handles it. Here we go. An example. Let's see how to do this together. Environmentalists, government officials, and vehicle manufacturers are all interested in studying the auto exhaust emissions produced by motor vehicles. The major pollutants in auto exhaust from gasoline engines are hydrocarbons, carbon monoxide, nitrogen oxides. Researchers collected data on the nitrous oxide levels for a random sample of 40 sample size, 40 light-duty engines of the same sample. The mean nitrous oxide reading was 1.2675, so that is our sample mean. And the sample standard deviation was 0.3332. Here we go. Construct and interpret a 95% confidence interval. Well, we have a lot of things on here that are already good to go. What do we have? We have our point estimate. Our point estimate is 1.2675. Our standard deviation is very close. All right, so things we need, things we have. Let's dissect the question. Things we have right here, x bar. We have right here is Sx. So how would I get this for the confidence interval? It would be 1.2675 plus minus t star. We'll get t star in a second. Standard deviation is 0.3332 over square root of 40. Now I just need my t star. T star will be on the calculator. What is the degrees of freedom? You always want to write df equals 39. df equals 39. So what do we have left? We'll just put t star there for now. We'll see on the next slide how to get it. But right from the question alone, a lot of here is done. Sample mean, standard deviation over square root of n, and we just get t star for a 95% confidence interval, and we will do it right here, right now. So we are going to write out the entire solution. All right? No shortcuts, no steps missed. State, plan, do, conclude. What do we want? We want to estimate the true mean mu of nitrous oxide emitted by all light-duty engines with a 95% confidence level. What are you trying to find? What confidence level? Plan. Name the test. If conditions are met, we will use a one sample t interval. There's the name of the test. We need to check for random. Yes, the data come from a random sample stated in the question. 10%. We are sampling without replacement, so we need to check that there are at least 400 light-duty engines. Yeah, it is safe to say there is at least 400 light-duty engines in existence. Large counts. Right here. Sample size is 40, which is greater than 30. We are safe to use the t distribution. We are safe to use the t distribution because we have 40 greater than 30. Now, everything written on this slide is not optional. It all must be checked. Okay? Next, we can do the question. I'm going to show you how to do the question, and I will show you how the book does way too much. So let's do the question together. Calculator open. If you wanted to know inverse t, just if you wanted to, it would be area 0.025 because it was 95%, so 2.5 on each side. Degrees of freedom here is 39, 40 minus 1. So will the book tell you that t star is negative, not negative, drop the negative, 202? Sure, it will. But do I need that? We'll see. The book tells you 202. It might even be a little bit different. Yeah, they're saying 204, 202, same crap. But what I wanted to tell you is you don't need that. It does not need it. Clear it out. Let's see what we do need. stat, tests. This is called a t-interval. The one sample t-interval, you'll see there's no such thing as one sample t-interval on here. It's just t-interval for one sample. And now this is where it gets a little confusing because it says, do you have data or stats? This is stats because you could see here that we have summary stats. So if they give you X bar, SX sample size, you have stats. They gave us all that. All our job is to type it in from computer or problem to calculator. Right here. The mean is 1.2675. 1.2675. Type it in. 1.2675. Standard deviation is 0.3332. So I type in straight from the question that SX is 0.3332. Sample size was 40. The confidence level 95. The calculator will handle everything. It will get T-star. It will tell you degrees of freedom is 39. It will do sigma over square root of n. So you don't do any of that. Nothing. Doesn't need to be done. You calculate it. You can see here that it gives you the answer, 1.16 to 137. So if I go back to the slides, let's state. Can I shortcut that? No. Plan. Can I make a shortcut here? No. Did I need to find T-star? This whole slide, not needed. The do step. The do step. I did not need any of that. You don't need to write any of that out. What you do need is the answer and degrees of freedom equals 39. This is your whole do step. Remember, we do things as state, plan, do. And now conclude. You need to be able to write this sentence out. It's always the same. We are 95% confident that the interval from 1.599 to 1.3751 grams per mile captures the, and then you put what it is, true mean nitrogen oxides emitted by light duty engines. That's it. You have to be able to write that form sentence. There is a lot of things you can skip. Remember, here was the problem. I could not skip the state. I could not skip anything in the plan and checking conditions. The do step, I didn't need T-star. I didn't need to show anything in the blue. I just needed the answer and the degrees of freedom. Look, the answer was right here in the calculator. 1.16 to 1.37. 1.16 to 1.37. See, same. Degrees of freedom, just take this and subtract 1. It's all there, plain as day, easy breezy, lemon squeezy. Let the calculator do the computation. Your job is enough. You have to write all this out, and you have to know how to write your conclusion. So that's all there. That's all done for you. How to do a t-interval. Okay, we're going to do another one now, except I want to show you that the calculator will be a big asset to you for other problems. Let's see now. A manufacturer of high-resolution video terminals must control the tension of the mesh of fine wires that lies behind the surface of a viewing screen. Too much tension will tear the mesh, too few will be wrinkles, nonsense. The tension is measured by an electrical, blah, 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 some variation, blah, 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 blah. Here we go. Here is the tension reading from a random sample, there's going to be random, of 20 screens right here. Okay, let's look at the major difference right away. Last problem we just did, they gave us the mean and the standard deviation. This problem that I put in, they gave you the raw data. So, raw data now, keep in mind. Okay, keep in mind with the raw data, you're going to be putting this in the calculator. You will go to stat, you will go to tests, you will go to t-interval. And this will just be data. And with data, all you need is List 1, you have to put the data in and tell it the confidence level. Frequency, just always leave it 1. So you would go to stat, you'd go to edit, list 1 would be all of this data. You would have to type it in. You'd have to type in every number. I'm not going to waste your entire day typing all these in, but how to do it on the calculator: stat, edit, type in the data when it is given to you, then stat, tests, t interval, and you have data. Now, a reminder, think about this. We're about to do our checks of conditions. Let's take a look. Random, we are told the data come from a random, okay? Plan, we will use a 1 sample t interval. Name the test, check the conditions, okay? So state, plan, do, conclude. I'm getting ahead of myself. First, let's state. We want to estimate the true mean tension of video terminals at a 90% confidence. So what do you want to find? What confidence? Plan, name the test, check the conditions. The test is a 1 sample t interval. Random was stated in the question. 10%. There are at least 200 video terminals produced. Sure, 10%. Now, normal. This is where it gets challenging because we don't have a normal population. We don't have sample size greater than 30. I'm not reading you all of this nonsense. So much nonsense, so much nonsense, so much nonsense. Stop here. Don't do all of this that the book says. What we would do is we would draw a normal probability to check normal or large counts or safe to use t. We would make a normal probability plot on the calculator, and you would still write the old-fashioned based on the linear trend of the normal probability plot. We are safe to use t calculations. Please don't be the people that ignore this video and do all of this random crazy work. Why are we doing this again? So the population, normal? No, not told to us. Greater than 30? No. Next, normal probability plot. That's the third option to assess normality when the first two aren't met, the easy two. Reminder how to make a normal probability plot. So I go to the calculator. Again, we're going to use the data, so you had to type it in no matter what. Stat edit, we already had typed it in. This isn't it. This is certainly not the data, but I'm just going to show you how to make a normal probability plot. It was second, y equals, we've been to stat plots before. You turn it on, you go to the sixth one, the one that looks like a normal probability plot. It says, is your data in list 1? It sure is. And then you do zoom, stat, zoom 9. Look at that. Nice linear trend. It doesn't matter. This data is totally different. Based on the linear trend of the normal probability plot, we are safe to use t calculations. Okay. How would I do this test? Look at this. All of this in the do step. I'm trying to make your lives easy here. All of this in the do step would not be needed. None of that. Do you have to know how to make a t interval? Sure. It is x bar plus minus t star sx over square root of n. You substitute all the numbers and you work it down. But you can use the calculator. Okay? You can use the calculator. Do you even need t star? No, you don't need t star. You would use the calculator t interval. So your do step, which would be before conclude, the do step would just look like this. df equals 19. Why? 20 samples minus 1 is 19. And then you would say the interval is 292.32, comma 320.32, because that's what the calculator would give you. It would hand you it in the t interval. All of this is extra work. Now, conclusion. This is not one you skip. You don't skip conclusion ever. We are 90% confident that the interval from 292 to 320 captures the true mean tension in the entire batch of video terminals produced that day. Of what? To steal that information right from the question. Okay. Choosing a sample size we'll come back to. This is how we ended last video. We'll end this one. But I want to draw your attention to your notes packet again for 8.2. Finding T-star instructions is written there. It's in your notes, the 8.2 notes, 8.3 notes, 8.3 notes today, right here. The next thing is, just like I showed you last time, the shortest way to do this, written out for you. Step 1, identify the population. What is the confidence level? Step 2, state the test you are using, 1 sample T interval. What are the conditions? SRS, could be stated in the problem, might have to assume it. Number 2, population at least 10 times larger than the sample. Right there, population 10 times larger than the sample. And then assessing normality, which was basically we say, can we use a T distribution? Okay, 1, could be stated that the population is normal. Number 2, use a normal probability plot, which we just showed you. Sketch a picture. Sketch the picture on your notes. And in number 3, if the sample size is greater than 30. This is for saying it's safe to use T distribution. The do step, this is it. I wasn't lying. T equals degrees of freedom equals DF equals, and then the confidence interval. DF equals, and the confidence interval. And step 4, conclude, proper conclusion. Okay? That's how you do these confidence intervals. We did it once with summary data. We did it once with raw data. You're going to see both of them live and in action. Last thing is, just like we did last section, if you were going to think about how many people you wanted to survey before you did a problem, and someone was paying you and you want to know how many people do I need to ask, let's take a look. Determine sample size to get a margin of error. Researchers would like to estimate the mean cholesterol level of a particular variety of monkey. They would like their estimate to be within 1 milligram. That's saying the margin of error, remember margin of error is critical value times standard error, will be within 1. 95% will be our confidence level. This is the key here. They can't ask you sample size without giving you something to use for sigma. Without an SX or a sigma, you can't do this. So they say, oh, in a previous study, the standard deviation you can use is 5. So it's not that hard because what happens is we also have no idea of degrees of freedom. Without sample size, you can't do degrees of freedom. So this is the only time you have to use a Z because you don't know degrees of freedom. So we'll use Z. 1.96 goes with 95. We learned that in section 2. 5 will be our sigma. And then once you put everything to its place, you say, okay, 1.96 is Z star, which is technically T star for means. 5 will be the standard error. They gave it to us. This has to be within 1 because they gave it to us. You solve this little algebra question and we say, oh, 96.04, always round up. We always have, so 97 monkeys will be our sample size. Does this seem really realistic? No, they could ask though. The textbook will ask this. Why is it not really realistic? Because you're using Z star. They have to give you this 5. They really have to give you a lot of information here. And the only thing missing will be the letter N. And that is it for 8.3. You're really going to want to practice all of your calculator commands. Remember, calculator, calculator, calculator for all of this stuff. Please don't just go with all of the craziness the book says. There's a much easier way to do these questions.